Okay. Well, everybody looks invigorated after spring break. So homework 3 was due today, and does anybody have any questions about it? Should be, this is a standard queuing model, should be that once you've done this homework, you have good understanding of how this stuff works. So there shouldn't be any questions. Well, I shouldn't say that before I ask if there are any questions. Are there any questions about homework 3? Okay, so what about homework 4? Yes?
It's been a little while since spring break.
Okay.
Go over the theory section of homework 4 again.
Okay. Okay, so the question is about homework 4. From the simulation point of view, homework 4 is simply an easy change from homework 1. So all you do is change the part where you generate the arrivals. And I showed you how to do that last time. I'll discuss it again if necessary, but let me go back over this theory. The theory, I think, is very interesting and is not generally not given enough attention. And in fact, it's not covered in the Bertzekis and Gallagher book, although all the other stuff that we're doing is covered to some extent in Chapter 3. And I want to remind you to be reading Chapter 3. You don't have to read it for detail. I want you to read it for context. So you can see that we're talking about the same thing. What I'm giving you is a little bit more detail and, in a way, I think a little bit easier than the way it's done in a little bit more gentle, although it goes deeper because there's more of it than what's in the Bertzekis and Gallagher book. So keep reading that. All right, now the model we're looking at is the model in which we have quasi-random input and block customers cleared. So hope we have some of these things at work. So to start off with, let's assume that we have a single source. And the way it works now is the source, let's say for the sake of argument, has a dedicated server. So the source is either in state off or on. So it could be off, on, and so forth. And you have what's called an alternating renewal process. And in our terminology, the off state is think time, and the on state is service. And what we'll say is that the average time in the off state is, or in the think state, is 1 over gamma, and the average time in service is tau. And we define A hat to be equal to gamma times tau. So gamma is the arrival rate when the source is thinking, and when the source is busy, the arrival rate is 0. And tau is the average service time. So this is like rate times time. So this is sort of analogous to offered load, but it's the offered load per idle source. Now, from this, we can calculate easily the probability that the server is busy. So let me call that, I'm going to give you 2 different notations here. First, I'll call it little p. That's the probability that the server is in the service state, or the source is in the service state. And that could be written as P. Wonder if we can get some markers here. Can I get some markers? Okay, so P is equal to, in our other notation, P11. In other words, in general, we're talking about the probability that in a system with S servers and N sources, you're in state J. Thank you. Okay. Okay, so we're talking about the case here where the servers are not limiting. And so this is then the probability that in a system with one source, that source is in the busy state, talking state, being served. And we showed before that that's equal to A tilde over 1 plus, or A hat, or whatever you want to call it. This is pretty greasy, I think. That's why this stuff isn't writing. Now, imagine that you're well, to start with, let's assume now that we have n sources and that the sources all have dedicated servers so that they operate independently of each other. Because if they have dedicated servers, then each source simply is either thinking in service, and so forth, and they're all operating independently because they don't interact because each one has its own server. And suppose I wanted to calculate the probability that of these n sources, exactly j of them are in the busy state. So now I would make the argument to say, well, this is simply going to be a binomial probability because each source is either busy or idle, that is either being served or in the think state. The probability it's being served or busy is equal to that. So therefore, the probability that out of n of them, exactly j of them are in that state would be p to the n, p to the j. I think the problem here is with the board, not with the markers. P to the j, 1 minus p to the n minus j, n choose j. And the argument there is, well, little p is the probability that a single source is busy, so the probability that of the n sources, exactly j of them are busy and n minus j of them are not, would be p to the j, 1 minus p to the n minus j. And then I would multiply that by the binomial coefficient, which is a number of different ways I can select the identities of the j sources out of n that are in the busy state. So this is the binomial distribution. And from the argument I made, it's clear that this then describes the state of this system, and it's valid for any distribution of think times and any distribution of service times. All that matters is the average think time and the average service time. Right, that should be clear because for an individual, if he doesn't interact with anything else, all he does is go from state off to on to off to on and so forth. The only thing that's going to affect the fraction of time that you're in either state is the ratio of the expected values of the time spent in each state. That is the time spent in the, for example, the average time spent in the on state to the sum of the time spent in the think state or the off state plus the on state. And I derived this previously. Is there any question about that? So now, if these guys are all independent, and they are because they have nothing to do with each other since they each one has its own dedicated server, so it doesn't interact with any others, then the probability that any j of them happen to be in the busy state would be given by this binomial distribution. Okay, but of course the whole point here is that you want to have a case in which there are s servers and s is less than n so that blocking can occur. So then the sources interact with each other because if a source makes a request for service and all the servers are busy, then that source immediately reverts to its think state, and so its state is dependent upon the states of the other sources. So therefore there's some interaction between them. So what are you going to do about this? So suppose that you're an intelligent engineer or physicist or applied mathematician in the days prior to when queuing theory became available. So you're going to use some reasonable answer. So you'd say, well, what I'll do is let me assume that these things actually are independent of each other, but for the sake of argument, that is, this is the best I can do at the time, what I'll do is I'll ask for the conditional probability that the number of customers or sources that are in the busy state is j, given that j is less than or equal to s. So let me write it like this. What's the probability that the number of busy sources is j if I know that that number is less than or equal to s? because S is the number of servers, and so of course the number of busy sources can't exceed the number of servers. So if I ask that question, but assume that I had otherwise this model, then I would say, well, that's by definition of conditional probability. By definition of conditional probability, that's the ratio of the probability of these two events jointly divided by the probability of the event on which I'm conditioning. So the denominator is the probability. I wonder if we can get this, can we get this thing washed or something? I don't think anybody watching this would be able to see what I'm writing on the board. Can you see that? I can't see it. On the screen you can see it?
Because the light's really hard to see with the naked eye, but on the screen you kind of get that light. It's still very light. Yeah.
Okay, my question is whether or not people watching this on the DVD, can we get this thing cleaned or something? Take a minute off here, because I don't think anybody can read this. I can't read it. Okay, we're going to take a cleaning break, I think. Okay, in the meantime, anybody know any jokes? All right, we're
Fast forward until you give this sign.
right. Well, they're not recording now. Yeah, right.
And that's what we're for. I hope you got all that.
Okay, we're back on. All right, so we've just had some kind of disinfectant here. We're cleaned off, so let's see how this works. All right, so where we were is that if all of these guys were independent, well, sort of works. The probability that of the n sources exactly j would be busy would be given by the binomial probability, the binomial distribution, where little p is the probability that a single source is busy, and we know what that is. And that does not depend on the distribution of think times or the distribution of service times, which makes it very robust. So now we're going to assume that we have an interaction. In other words, now I'm going to assume that there's a number of servers S where S is less than n. N is the number of sources. So I'll ask this. What's the conditional probability that the number of busy sources is equal to j, given the condition that n must be less than or equal to s because there are only s sources? And remember that in our model, the blocked customers are cleared. So whenever someone makes a request for service, if they find all the servers busy, they revert to the think state. Okay, so by the definition of conditional probability, that would be the ratio of two probabilities. The denominator is the probability of the event on which I'm conditioning, and the numerator is the probability of those two events jointly. In other words, it's the probability that the number in service is equal to j and the number in service is less than or equal to s. Now, the only way that the number in service can be equal to j and be less than or equal to s is that the number in service must be j, where j is a number that is less than or equal to s. So the conditional probability reduces to that. The numerator then is exactly what we wrote here. N choose j, p to the j, 1 minus p to the n minus j, divided by the sum of n choose k, p to the k, 1 minus p to the n minus k, as k runs from 0 to s. Okay, so this would be the conditional probability if in fact these sources became busy and idle independently of each other, but of course we know that they don't. But it seems like it might be in a reasonable approximation. Okay, now we know something about queuing theory, and so we look at the case of the birth and death process when the input is quasi-random and the service times are exponential. And we write the rate up equals rate down equations. So in other words, we're going to assume that when I'm in state J, the instantaneous arrival rate is n minus j times gamma, where what this says is that the instantaneous arrival rate or birth rate is proportional to the number of sources that are eligible to make requests for service. So if I'm in state J, n minus j of them are in the think state. The request rate per idle source is gamma, exponential think times. So therefore, this would then correspond to the instantaneous birth rate in the birth and death process. We make the similar assumption for the death coefficients. Mu j is equal to j times mu, where mu is equal to 1 over tau. J times 1 over tau, assuming that we have exponential service times, and we solve the equations. And then we saw that when we solve the equations, the result is exactly this result right over here. Pj of n turns out to be equal to n choose j, p to the j, 1 minus p to the n minus j, divided by the sum, n choose k, p to the k, 1 minus p to the n minus k, as k runs from 0 to s. And this is the equation that's in the textbook, and it's equation 7.5. This is for j equals 0, 1, up through s, 7.5 in the book. So now we have the strange fact that when we solve the equations for the case of all the underlying distributions being exponential, we get exactly what the intelligent engineer would have gotten if he didn't know anything about birth and death processes and just made the most reasonable approximation that you could think of. Well, that indicates that it's conceivable that even though this was derived for the case of exponential underlying distributions, maybe, as in the argument that was made here, maybe this is actually more robust than that, and maybe it'll in fact hold if the service times are not exponential or the think times are not exponential. And it turns out that that's true. That was proved in the 50s by J.W. Cohen, and what I'm asking you to do in the homework is to verify that. So in the homework, I ask you to simulate this, and then to run the simulation for 3 different cases where the think times are exponential and the service times are exponential. In that case, we should get this result. And then to run it for the case where the think times are where the think times are exponential and the service times are constant, and then for the case where the think times are constant and the service times are exponential, and it will turn out, if you do the simulation, that the results appear to be the same. And that would support Cohen's theorem, which says that these results are insensitive, amazingly, in my opinion, totally insensitive to all of the underlying probability assumptions you might make. And that makes this model, if it's applicable, it makes it very robust, because that means that you don't have to worry about whether or not the underlying distributions are exponential. It doesn't matter whether they're exponential or not. So that's the purpose of homework 4, and I gave you this citation for this paper by Hyman, Lachman, and Neidhart, which actually uses this model and claims that it fits data for internet traffic, in which the sources are simply represent on-off sources that are generating messages, and they claim that one of the arguments in favor of its use, not only that it happens to fit the data, but also that it is insensitive to the underlying distributions. So this is what I want you to figure out. Now, the simulation is straightforward because it's exactly this, almost exactly the same simulation as what you did in homework 1, except that you generate the arrival process differently. But everything else is the same. Is there a question there?
That will look exceedingly complex and Instructor wrote. Is there a easier way to determine that? Like, I think, did you have a iterative?
I didn't give you a one. I gave you an iterative one for the Erlang B. But the same kind of argument applies here. So you should be able to calculate for the binomial. You should be able to calculate the probabilities iteratively, that is, or recursively, as you let the value of n and j get larger and larger. So you should be able to figure something like that out. But actually, I don't think this would be a problem in this case, because the j value is always going to be less than or equal to s, and s is only 10 in our case. The n value, of course, is going to grow. So you have two problems. You've got the theoretical computation problem, in which I give you the formulas, but it may be difficult to get the answer with good accuracy, good precision. The other problem is that when you run the simulation, even though the code is the same, the larger the number of sources, the longer you're going to have to run it in order to have things stabilize. For example, if I had 1,000 sources, let's say, then if I ran it for 1,000 requests, I would still probably not have generated a request for every single source. So there could be practical problems in terms of how fast the simulation runs. And in that case, I'm not sure what to say. Just do the best you can. If you have patience and you have a computer, well, let it run. For the cases where n is small, it should be easy. And if you get agreement between theory and simulation when n is small, then any disagreement you would get when n is large is probably because you haven't run it long enough. So if you can run it for large values of n, that's great. But that's not really a critical factor. The thing I'm trying to illustrate, though, by asking you to do it for large values of n, is to show you that as n goes to infinity and the offered load per idle source goes to 0 in such a way that the total intended offered load remains constant, that the results are all going to approach the value you would get if you had the ordinary Erlang B model with Poisson input and arbitrary distribution of service times. So I'm trying to show this convergence there. All right, now, in order to do the theory, what do you need to know? Well, you want to be able to calculate this formula right here, which means you got to calculate the p, and the p, the little p, is equal to a hat over 1 plus a hat, where a hat is the offered load per idle source. Gamma, remember, and tau are the primary parameters. Okay, now also, you want to be able to calculate the utilization. And the utilization, by definition, is the carried load divided by the number of servers. So that means you need to be able to calculate the carried load. Now, there's a formula that's given in the book, and remember, carried load, by definition, is the average number or expected value of the number of busy servers. So since you have the state probabilities, you can take the state probabilities and plug them into the formula for average value, and then after that it's just a matter of arithmetic. And if you do that, not that it's important, it's just arithmetic, then you will get the following result. A prime is equal to A star, that's the intended offered load, times 1 minus S over N PS of N. And this is equation 7.8 in the textbook. Okay, now what's A star? Remember, A star is the intended offered load. Oh, there's a question. Yes? Excuse me? No, A star equals. This is equation 7.8 in the book. So if I, excuse me, you're right. The equals is over here. So if I want to calculate the carried load, I multiply the intended offered load by these guys right here. This, of course, is one of these probabilities. So this is a formula for that. Okay, now what's A star? A star is the intended offered load. By definition, that's the load that the sources want to offer, in the sense that if they had dedicated servers and there was no blocking, then this is the load that would actually occur. Now, the true load is going to be different from that, because when sources offer requests for service, if they find all the servers busy, then they immediately revert to their pre-request state, to their think state. and that makes them eligible to generate another request earlier than they otherwise would be, which means that the actual offered load is going to be larger than the intended offered load if the block customers are cleared. That's because of the feedback effect, or the effect of retries, you might say. Okay, so what is the intended offered load? Well, if all of the servers were dedicated, then the state probabilities would be given by this numerator. It would just be the binomial distribution. And the expected value of that is n times p. And p is equal to a hat over 1 plus a hat. And so that's the formula for the intended offered load, and that's given in the book somewhere. In fact, I think it's given in the beginning of the chapter. It's equation 5.2. Now, in your problem, the intended offered load is 9.6 Erlangs, because I want to compare this. You have 10 servers. And so I'm trying to compare this with the infinite source model, which is the one that we did in homework number 1. So if I let the intended offered load be 9.6 Erlangs, then in a limit as n goes to infinity and gamma goes to 0 in such a way that, the total offered load remains constant, then this will converge to that model. Now, what is the actual offered load? Let's see, I think I'll write it over here. I said that the offered load would be different from what you would, from what the intended offered load is because of the feedback. And I can get the offered load easily by using Little's theorem. So this is equation 7.9 in the text. And there the argument is that the carried load is equal to the offered load times the fraction of the offered load that's carried. And that's 1 minus pi s of n. The reason this is Little's theorem is that A, this guy right here, is the arrival rate times the average service time. So this then represents the entry rate, the arrival rate times the fraction of arrivals that are not blocked. So that represents the rate at which they enter the servers, and the average time they spend in the servers is tau. And then if I call lambda times tau A, that gives me the actual offered load. So once I have the state probabilities, from the p's I can calculate the pi's. I can put them in here, and I can also calculate the carried load directly from the definition of the probabilities. And so therefore I can figure out what the actual offered load is, or equivalently what the actual arrival rate is. And of course the actual arrival rate will not be the arrival rate per source times the number of sources, because we don't know what the arrival rate per source is. The gamma is the arrival rate per idle source. So this allows you then to calculate everything. Okay, now, how do you get the pi's from the p's? And the answer is, well, we proved in class that the probability that in an n-source system an arrival finds a system in state J is equal to the probability that in an n-1 source system, the outside observer would find the system in state J if he samples at random. So this was an interesting theorem. From a practical point of view, it may not make much difference if n is large, but from a theoretical point of view, it's an interesting relationship, and it reflects the fact that the pi's and the p's are not the same. And that's one of the things I ask you to check in the homework. That is, to calculate the pi's and calculate the p's for state S, and do it through the simulation. And remember, in the simulation, the pi's represent the fraction of customers who find the state, just as in homework 1, and the p's represent the fraction of time the system is in that state, just as in homework 1. But in homework 1, when you had Poisson input, those things were equal. That's the pasta theorem. Here we don't have Poisson input, So these things are not equal, but it turns out that if you replace the n by n minus 1, then it works, and we proved that in class. So what I'm asking you to do is to verify that by calculating what the theory predicts and then comparing it with simulation. And of course, if you do it right, everything will work out. Okay, so that's the theory. Then the simulation is exactly the same as it was in homework 1, except for the part where you generate the request for service. And instead of generating them according to a Poisson process, you generate them according to this algorithm that I gave you by looking at each individual source and describing its state. Do you want me to discuss that, or is that anybody need to? You want to see that? But you're afraid to ask out loud, right? Okay, when I said to the, does anybody want to see that, there were several people who said yes, so okay. Any questions about this? Okay, so this is the theory. Okay, simulation. Simulation is, we've got these servers. I'll call them server 1, 2, and 3. And what we did in homework 1 was we had 2 urns. The only one of interest at this point is the inter-arrival time urn. So we had inter-arrivals, and we imagined that there were tickets in there. And what we did is, well, we pulled a ticket from the inter-arrival time urn, and that told us when the first arrival is going to occur. And then we would look for a server, and if the server was available, then we would pull a ticket from the service time urn, and we would make the server busy for that length of time. And then we would pull a ticket from the inter-arrival time urn to get the next arrival. In this diagram, it would be server number 2, then the next one might be carried on server number 3, and so forth. So this is the state diagram. Okay, now, instead of generating the arrivals by picking from this inter-arrival time urn, which makes the inter-arrival times independent, identically distributed, now the arrivals are generated by these individual sources. So now what I do is I have for each source, I have an element in an array. So maybe this is source 1, source 2, source 3, and so forth, source n. And now, for each source, I'm going to keep a record of when that source is going to make its next request for service. So let's say here's source 1, here's source 2, here's source 3, source n, let's say. Okay, now in homework 1, I would come over here and I would draw a ticket, a value for an inter-arrival time. In homework 4, now what I do is I look at all my sources and I find the source which is the smallest in terms of the length of time remaining until it makes its next request for service. So in this picture, it turns out to be source number 2. All right, then I generate okay, now I'm going to move my clock over here to the time at which source number 2 makes his request for service, and then I generate that arrival. Now, there are 2 possibilities. One is that when I generate this arrival and look for a server, it finds an idle server. In that case, the time at which this guy is going to make his next request for service is going to be the service time that he's going to experience plus his think time. Or writing it backwards, there's going to be a think time plus a service time. Which means that when I update the state of the servers, then, and I look to generate a next request for service, and I search for the minimum, this guy's time at which he's going to make his next request for service is right over here. But another possibility is that when he makes his request for service, all servers are busy. If that happens, then he immediately reverts to his pre-request state, to his think state. And when he reverts to his think state, that means that he has no service time, but he has a think time. So therefore, I update him by his think time, but I don't add in a service time. So what it amounts to is that whenever I generate a request for service, I look through my sources and I find the one that is next scheduled to make a request for service. Then I generate for him a think time. And in addition, I look to see whether or not he's going to be carried on this request. If he is, then I also generate a service time. If not, then I don't generate a service time. And that's it. Then I go back, I handle the request just as I did in homework number 1, and then when I'm ready to generate a new request for service, I go through this new updated list, pick the minimum, and everything is repeated. Okay? All right, so that's the only difference, and when you run the simulation for the various different cases, the only difference from one case to the next is whether the think times are exponential or constant, and whether the service times are exponential or constant. And according to our theory, it shouldn't make any difference in terms of the final results, which, as I say, is an amazing result. Okay, so everybody should be up to date now. That should explain everything you need to know about homework 4. Has anybody actually tried to run a simulation for homework 4? I take that as a no, right? How about the theory for homework 4? Partly, huh? Okay, so are there anything else I could tell you about homework 4? Is it reasonable to make it due in a week? Okay, a week means that you have time to ask questions on Wednesday, and then you have the weekend to work on it. Okay, so let's make it due a week from today, but if necessary, a week from Wednesday. So you have another time at which to ask questions. Okay, but this should not be a hard problem. If it is hard, it's in the actual running of the simulation program or the calculation of the probabilities, which of course should all be done by computer, not by hand. You don't want to sit down there with a calculator and start calculating p to the 10 or something like that. Okay, the next model is the one in which the block customers wait in a queue. So I didn't give you a homework problem about this, but it's no big deal. Now, there is a difficulty here in that now the state probabilities are more complicated. Okay, so let's see. So now I'm doing the analog of the Erlang delay model, but with a finite number of sources. So now, so I'll say blocked customers delayed. Okay, so this is the analog of the Erlang delay model. The model we just looked at was the analog of the Erlang B model. This is the analog of the Erlang C model. Okay, so in this case, we say that the birth coefficients are the same as before, quasi-random input, just like before. What about the death coefficients? Well, now this is the difference. Previously, the highest state was state S, all servers busy, and as long as I was in the state less than or equal to S, then the aggregate death coefficient was J times mu, or J over tau. But if J is greater than or equal to S, then those remaining sources are waiting in a queue. And so the aggregate death completion, service completion rate, or death rate, would be S times mu. J is greater than or equal to S. Just like in Erlang C. So the end result is that this makes the arithmetic more complicated, and the numerical solution is given by equations 8.3 and 8.4. P, J, N. So 8.3, 8.4. So it's more complicated, but it's still just a formula. All right, but now, just like with Erlang C, we want to calculate something about waiting times. So I want to calculate the probability that the waiting time is greater than t. And we do that the same as before. You say, well, that's the probability that the number that you find in front of you is j times the probability that the waiting time is greater than t given that the number you find in front of you is j, summed over all j. This part is new. That's the results of these state probabilities. Actually, what this would be pi j of n, the probability that when I make a request for service, I find j in the system ahead of me. And of course, the pi's are calculated from the p's and then with n replaced by n minus 1. What's the probability of waiting greater than t given that you find j in front of you? Well, here are your servers. Here's your queue. Let's say that in front of you you find some number in the queue, k, j altogether, k in front of you in the queue. What's the probability that you wait greater than t? And now my claim is that this answer is exactly the same as it was previously, as it was for the case of the Erlang delay model. Because once you condition on a number in front of you, all that matters is the completion process. And if you have exponential service times, we already made the argument that the times between departures are exponentially distributed because it's the minimum of the exponential service times. So the bottom line is that this probability here is exactly the same as it was previously for the ordinary Erlang delay model. So the answer is going to be more complicated because these guys are more complicated than they were before, but it's just arithmetic. And in fact, believe it or not, it's shown in the textbook that equation 810 answers it. So there's a lot of algebra involved here, but it's interesting to write down what the answer is because it has a nice form. So we're equation 810 in the book. The probability that with FIFO, of course I'm talking about FIFO service here, that you wait longer than t is given by something, let's see, it's c, a constant, times the summation as j runs from 0 to n minus s minus 1. And then inside there you have something like this. You have phi of t to the j over j factorial e to the minus phi of t. In other words, the phi function is given in the book, and it's a function of t. Actually, it's phi of t is equal to s mu. Here it is. Phi of t is equal to s mu over gamma plus s mu t. So it's easy to compute. So what's interesting here is that despite all of this complicated looking arithmetic, when you get all done with it, this probability is a sum of Poisson terms because it's of the form sum to the j over j factorial e to the minus something. So once you calculate the constant, which is given in the book, and plug in the value for phi of t, you just add up Poisson terms, and that gives you the waiting time distribution function. Okay, any questions about that? All right, so I'm not asking you to compute this one, although it's no big deal. So in fact, I think in most of the literature, it's this model, which is the case where the block customers wait in a queue, that's considered to be more important in applications, but I'm not sure that that's really true, especially in light of this, the paper by Hyman, Lakshman, and Neidhart. Okay, so I tend to like the other model better because it's neater, and if it also has applications that are modern, well, that's even better. Now, sometimes this model is represented this way. I have a bunch of sources, and the sources make requests for service, and I have a server or servers. I'll just put it like that, S servers. And then if the servers are busy, then the sources queue up, and then as soon as they finish their service, they simply cycle back and instantaneously return to the think state. And so this, in fact, is the simplest example of what's called a closed queuing network. So it's closed. The sources simply cycle around here. And one of the questions you want to ask is, if we have the waiting time distribution function, how are we going to calculate, for example, the average waiting time? And it turns out that there's really a nice way to do that. And this is given by equation 820 in the textbook. And it uses Little's theorem. Okay, so let me illustrate this. In a classical computer science model, these are terminals, and this is a CPU, or maybe multiple CPUs. And when a terminal wants to use a CPU, if the CPU is available, he holds it for his processing time, and then cycles back to his think state. And if the CPU is busy, then he waits in a queue, and then gets his processing time, and then cycles back to his think state. And so the question is, well, what's the throughput of this system, and what's the average time that you spend waiting or in process? And Little's theorem answers the question very neatly. It says, well, why don't we look at it like this? Why don't we imagine that there's a break here, and that what happens is that we're going to view this right here. And so we can say that when a customer leaves the servers, he leaves the system, and then he instantaneously re-enters the system. So therefore, the output from here, which is called the throughput, that's the number of jobs served per unit time, that's also equal to the arrival rate, because everybody who is throughputed through here immediately re-enters the system. So if I write L equals lambda W, okay, so here is my L equals lambda W. That is, average number in system is equal to the rate at which you enter the system times the average time you spend in the system. That's Little's theorem. It has nothing to do with the underlying distributions. That's its beauty. Okay, now, let me write that. L is n, the number of sources. It's not just the average number, it is the number. So however many sources there are, that's the average number in the system. That's equal to the rate at which they enter the system, which is lambda, which is also the throughput, times the length of time it takes them from the time that they enter until the time that they leave. In other words, the time it takes to go from there around to there. Okay, well, how long is that? Well, first of all, there's the length of time that they spend traveling from there to there, which is 0. They do that instantaneously. Then there's the length of time they spend in the think state. That's 1 over gamma. And then there's the length of time that they spend waiting or in the queue. That's called the sojourn time, and is often written E of t, t for sojourn time. So the sojourn time, t, is equal to, by definition, waiting time plus service time. In the computer science context, the sojourn time is more important than the waiting time, because you don't care how much time you spend in each part of the sojourn time. All you care about is how long it takes you from when you make your request for service until it's honored, until it's finished. So in any event, what this shows is that I now have a relationship which relates the number of sources, the throughput, the think time, the average waiting time, and the average service time. So presuming I know the average service time and I know the think time, then that gives me a relationship between the throughput and the average waiting time. So it doesn't tell you what either of those is, but it tells you what the relationship is. So it's easy to draw a graph which relates the throughput to the sojourn time as a function of the number of sources. And in fact, that's done in the Bertsekis and Gallagher book. All right, so this is really a neat application of Little's theorem, because in order to calculate this expected value, you don't have to go through all this arithmetic. And furthermore, it has in it the throughput, which in itself is not has to be calculated from the probabilities. So what this says then, if I have the energy to calculate the average time it takes to go through the system from the state probabilities, then from that I can also calculate the throughput. And shows exactly what the relationship is. It's what you would call a conservation law. Okay, so this is equation 820 in the textbook. In fact, in that page, it's some numerical examples are given. And that now ends this chapter. And so now I want to start on the next chapter, a whole new different topic. So before I do that, are there any questions about where we stand now? All right, so to summarize the course so far, what we've done is, after developing a lot of theory, we looked at the general birth and death process and saw how that could be related to queuing models. And in particular, we looked at two particular models, one in which the block customers are cleared, and one in which the block customers wait in a queue. And for those models, we calculated everything, and then we saw that we compared the theory with the simulation for several cases, and if you did the homework, everything works out, and everything should be clear. That is, what should happen is you should understand exactly what it is that the theory is calculating. And furthermore, we illustrated that it's not just a matter of arithmetic. A lot of textbooks in this subject seem to get bogged down with just listing different models and then big formulas for each model. But I don't think that's the important thing. The important thing is the insight. And there's a lot of insightful results and a lot of surprising results. And the simulation is designed to elucidate that. Okay, so now we've done the basic stuff of elementary queuing theory. So is everybody satisfied with that, or? So. Any questions? Anything I can answer about it? Fill in any details? Okay, so I assume everybody is okay with homework 3. And once you do homework 4, then I think it'll be clearer, because then you'll see the finite source effect. And now we can go on to something that's a little bit more advanced. Although, well, I guess it's more advanced. It's actually more surprising, maybe more interesting. And in this book, it's entitled Multidimensional Birth and Death Queuing Models. But basically what it's going to reduce to, what's going to result in, is what's called queuing networks. So by multidimensional, now I'm going to be talking about cases where you need more than one variable in order to describe what's going on. So instead of having, for example, well, here's what we'll get to shortly. There's basically two kinds of networks. One is called a circuit switching. So it looks like this. I might have, here's a simple example. Here is city A, B, and C, and I have a bunch of trunks, servers connecting A and B, and a bunch of trunks connecting B and C. And now if I looked at each trunk group in isolation and assumed that the only traffic here was traffic between A and B and traffic between B and C, and if the block customers are cleared, then this is just two Erlang B systems. But to make a network out of this, to make this more interesting and more realistic, what we want to do is assume that if a call wants to go between A and C, that it'll hold a trunk or a server or a channel between A and B, and simultaneously a channel between B and C. So that means that in order to represent what's going on here, I need to have at least 3 variables. I need to know the number of customers between A and B alone. I need to know the number of customers between B and C alone, and I need to know the number of customers between A and B, between A and C, because those guys are interfering with the guys between A and B and the guys between B and C. Now, similarly, I could have the case in which instead of circuit switching, instead of having ordinary telephone calls, these represent messages and maybe packets. And then we would say that we could model this to say that if all channels or servers are busy here, then a queue forms, and the packets are then sent from there to there, and if everybody's busy there, then a queue forms again, and so forth. So in the packet switching case, or the queuing network case, the queuing network, as opposed to the circuit switch network, then what you have is a bunch of queues in tandem in which the input to one queue is the output from the preceding queue. So they're two separate cases. So one corresponds to a generalization of the Erlang loss system, and the other corresponds to a generalization of the Erlang C, or Erlang delay system. And it looks like this is very complicated. In some sense, it is very complicated, but there's some amazing simplifications. And in fact, if you look at the literature now, there's a subject which is almost separate from queuing theory, which is called queuing networks. And if you go to the web and type in queuing networks, or go to Linka's queuing theory page, which I mentioned earlier, you'll see that there are books, many books now, devoted solely to queuing networks. And both of these kinds of networks are addressed in the Bortsekis and Gallagher book. So again, look at Chapter 3 and see in Chapter 3 where what I'm doing corresponds to what's covered in that book. Okay, so let me start off by giving a simple example. Suppose that we have an infinite number of servers, and we have 2 Poisson streams. Okay, so here's my model. So there are my servers. And let's start off and say that, okay, I've got a Poisson stream, and let's say that it arrives with rate lambda 1, and it has exponential service times with rate mu1. And there's another Poisson stream which arrives with rate lambda 2 and has exponential service times with rate mu2. So we'll call this A1 Erlangs of traffic, and this is A2 Erlangs of traffic. So the arrival streams must be, at the moment, Poisson, but they have different rates. For example, this might be data traffic, and this might be voice traffic. And they have exponential service times at the moment, but they have different expected values, different service completion rates. So we want to be able to describe what's going on here. So I'll do that by representing the state by P of J1, J2. In other words, J1 is going to be the number of customers from stream 1. J2 is going to be the number of customers from stream 2. And what I want to get is I want to get the joint probability, and then from that get the marginal probabilities and everything else. Okay, this stuff is discussed in the book. So this is section 4.2, page 126. Section 4.2, page 126. Okay, now here's the strategy for analyzing a system like this. And by the way, I might add that if you look at the website for the course, the remaining homeworks, except for the last one, are up. And they don't have anything to do with queuing networks. So what I'm doing is I'm asking you to examine carefully the standard one-dimensional queuing models. We've seen some of them already, and I'll discuss more as we go on. And while you're doing that, I'll be discussing these multidimensional models. So this is important and interesting, but I'm not asking you to do a homework, except maybe at the final, but I don't know about that yet. But there's no homework that relates to this. So keep that in mind. That is, I'm not worried about the detail here. I'm more interested in some insights and strategies, and that the detail will still be what we've been doing in the course so far. So we'll be looking at relatively simple one-dimensional models, and each homework will be a little bit of a step in theory or a little bit change in the simulation. But right now, in parallel, I'm going to do this stuff with multi-dimensional models. Okay, so here's the idea. I'm going to represent the states of the system by this grid. I can do that as long as I have only two variables. So here is J1, and here's J2. And here are the values you can get. So 1, 2, 3, 4, and so forth. 1, 2, 3, 4, and so forth. So every state is a point here, like this. So this represents a state, J1, J2. So here are all my states. Now, what I did previously when I analyzed one-dimensional systems was we said the rate at which the rate up from each state is equated to the rate down from the state below it. So I had rate up equals rate down. Now I don't have up and down, but I'm going to define instead in and out. So I'm going to imagine that I take some target state, which I'll call J1, J2, and I want to equate the rate at which I leave state J1, J2 to the rate at which I enter it. Okay, so here is state J1, J2, and so I'll imagine that I draw a circle around here, like in physics where you have flux. And then I'll say, okay, now, I leave that state and I go from it to neighboring states, like there, and so forth. And so I imagine that I'm going to equate the rate at which I flow across this boundary, the rate at which I leave it to enter neighboring states, to the rate at which I cross the boundary going in the other direction from the neighboring states. So what I have is for each state, rate out equals rate in. And I'm going to make the same kind of assumption I made before for the one-dimensional birth and death process, which is that every transition is simply a single arrival or departure. In other words, I'm not going to allow multiple steps, so that at each instant in time, either I have a birth or I have a death, but now there can be different kinds of births and different kinds of deaths. Okay, so here's the particular example. I now have two different streams of traffic with different parameters. P J1, J2 is the probability that I have J1 customers from stream 1 and J2 customers from stream 2, and I'm going to equate the rate at which I leave this state, J1, J2, to the rate at which I enter it by means of a single transition from neighboring states. So I'm not going to go through the details for the birth and death process because the details get complicated, but by analogy, it's simply the same kind of reasoning as was used for the one-dimensional birth and death process, except that we have more variables. Okay, so how can I get out of this state? Well, I can have an arrival from stream 1 or an arrival from stream 2. And remember, when we wrote rate up equals rate down, what we did is we multiplied the arrival rate at which I go up, to the fraction of time I'm in the state, and that gave me the rate at which I went up a step. So now I'm going to have the rate at which I go out a step. So this is the rate at which customers from stream 1 arrive. This is the rate at which customers from stream 2 arrive. And of course, a customer from stream 1 arriving will make J1 be J1 plus 1. A customer from stream 2 arriving will make J2 go to J2 plus 1. Likewise, I could have departures. Well, if I'm in state J1, J2, and I have exponential service times, then the rate at which the customers from stream 1 leave the system, that is, go to neighboring states, is going to be J1 mu 1. And the rate at which, aggregate rate at which customers from stream 2 leave the system is J2 mu 2. So we have exactly the analogous thing we had before, except that now we have to consider the two different streams. So this is the rate out from state J1, J2. Okay, now what's the rate in to state J1, J2 from the neighboring states? Well, what are the neighboring states that are one transition away? I could be in state J1 minus 1, J2, and have an arrival from stream 1. Or I could be in state J1, J2 minus 1, and have an arrival from stream 2. Or I could be in state J1 plus 1, J2, and have a departure from stream 1. That rate would be J1 plus 1, mu1. Or I could be in state J1, J2 plus 1, and have a departure from stream 2, and that rate would be J2 plus 1, mu2. Okay, so I equated the rate at which I leave state J1, J2 by either arrivals or departures to the neighboring states to the rate at which I enter from the neighboring states. And these are the states, in this case, that I could be in and travel from that state to that state by a single arrival or departure. So rate out equals rate in, no big deal, exactly the same kind of reasoning we did before, just a little bit more complicated in detail because there's more variables. But the difficulty is that I have to solve these equations, and I can't solve them by successive substitution as we did before. Now I have to solve them simultaneously, so this can be a big deal. But it turns out that there are amazing simplifications. So let me start with the first one. So I'm going to solve these equations, but I'm going to solve them initially by a trick. That is, I'm going to observe something, write down the solution, and then see how the solution works. So here's the way I'm going to do it. Imagine we looked at our servers, but now I'm going to break them into two groups. I'm going to have server 1, 3, 5, and so forth, and server 2, 4, 6, and so forth. I can do that because in this case, since I have an infinite number of servers, there's not going to be any interaction or any blocking because no matter what state I'm in, there's always going to be room for another customer. So that means that if I'm only interested in the total number of customers of each type, I could say that all the customers from stream 1 are dedicated to the odd number of servers, and all the customers from stream 2 are dedicated to the even number. Okay, so this is lambda 1 over mu 1, or A1, and this is lambda 2 over mu 2, or A2. Now, obviously, the number of customers from stream 1 and the number of customers from stream 2 are independent of each other because they don't interact with each other, because there's always room for another customer. So there's no interaction between or competition between the customers from stream 1 and customers from stream 2. So therefore, I know that the joint probability that I have J1 from stream 1 and J2 is the product of these marginal probabilities because obviously they're independent. So now the question is, well, what's the probability that from stream 1 I have exactly J1 customers, and from stream 2 I have exactly J2 customers? And the answer is, well, we've already solved that problem before. That's the one-dimensional case. And we saw that we have a Poisson distribution for the number of customers present if I have a simple set of servers with an infinite number of servers. So in other words, P1 J1 would be given by lambda 1 over mu 1 to the J1 over J1 factorial, and times a constant, a normalization constant. And P2 would be lambda 2 over mu 2 to the J2 over J2 factorial times a constant, and I'll just call the product of those constants a constant C. So in other words, because the random variables that represent the number of customers from stream 1 and stream 2 don't interact with each other, they're independent, therefore the joint probability has this so-called product form. And so I know what the answer is. So therefore, if I took this formula and plugged it into this equation, it must satisfy it. So let's do that and see how that works. So let's pick a term on the right-hand side, plug the solution in, and see what happens. Somebody pick a term on the right-hand side. Any term. How about this one? As good as any. Okay. So what I want to do is I want to calculate J1 plus 1, mu 1, P of J1 plus 1, J2. Based on the joint probability being given by this formula, which we got, which is clearly the correct answer as long as we have an infinite number of servers. Okay, so what do we get? We get J1 plus 1 mu 1. All right, now what do we have here? We have lambda 1 over mu 1 to the J1 plus 1 over J1 plus 1 factorial times lambda 2 over mu 2 to the J2 over J2 factorial times the constant. And now I'm going to cancel out the J1 plus 1 with the J1 plus 1 factorial, making that a J1 factorial. So what's left? Well, in the denominator here, I have J1 factorial. In the numerator, I have lambda 1 to the J1 plus 1, which I'm going to write as lambda 1. And then here, lambda 1 to the J1. So lambda 1 to the J1, that's lambda 1 to the J1 plus 1. Then I have a mu 1, and in the denominator, a mu 1 to the J1 plus 1. So I'll cancel that mu 1 with one of those guys, and that's going to leave it to the power J1. I'll keep the rest of it the same. Lambda 2 mu 2 to the J2 over J2 factorial C. So what I did was I canceled that term with that, simplified that, and rewrote it. So this numerically is exactly the same as that, algebraically I should say, and equals that. But what is that? Well, this part right here is exactly P of J1, J2. So what I showed was that this term right over here is exactly equal to this term right over here, that times that. Now, we already know that since this is the solution, if I plug the solution into the original equations, the left side has to equal the right side. That's what solution means. But I've showed more than that, because the equation only requires that the sum of the terms on the left equal the sum of the terms on the right. But I just showed that a particular term on the left equals a particular term on the right. Okay, now you can see immediately what's going to happen. Because when I plug in the known solution into here, that term is going to be algebraically the same as this one. And similarly, this term is going to be algebraically the same as that one. And this term is going to be algebraically the same as that one. So we know that the product solution satisfies the equations, but more than that, we know that the product solution satisfies the equations on a term-by-term basis. Now you might say, so what? Because we just solved a problem that nobody cares about, because it's a problem where we have an infinite number of servers. And if we have an infinite number of servers, then no blocking ever occurs, so who cares? The whole thing is not very interesting. But the reason for doing this is because it'll turn out that that in lots of cases, even when there is an interaction, that the same results hold, even though the streams are not independent of each other. For example, when I go through these network problems, we'll see that we also have product solutions, but obviously the streams are not independent of each other because they compete with each other. Okay, so let's go back to this problem now, and let's change it slightly to make it more interesting. Let's say that now we don't have an infinite number of servers. Now we have a finite number of servers. Okay, so now these probabilities represent the number of customers from each stream that's being served. Let's assume that block customers are cleared. But clearly, the number of customers from stream 1 and the number of customers from stream 2 are not independent of each other. Because, for example, if I told you that there are S customers from stream 1 in service, then you know that there can't be any customers from stream 2 in service, because the total number of customers in service can't be more than S. So the question is, how do I solve this problem? So I'm going to get back to this next time. Just let me say quickly what's going to happen. What's going to happen is that when I write the equations, if you think about it, the same equations are going to apply as long as the condition that J1 plus J2 is less than S holds. In other words, as long as the total number of customers present is such that a customer from either stream has room to be handled, then the state equations that represent the transitions is going to be exactly the same. But what happens if I'm on the boundary? If J1 plus J2 adds up to S, then a customer from stream 1 who arrives will be cleared and will not cause a change of state. And a customer from stream 2 who arrives will be cleared, will not cause a change of state. So in fact, I'm going to have different equations on the boundary. In other words, I could draw a picture like this, and there's going to be a boundary here. This line corresponds to J1 plus J2 equals S. In other words, all of the nodes that I intersect with this line correspond to all servers being busy. And so I have a boundary condition, which means that these equations are going to describe the state of the system on the interior of this diagram, but along the boundary, I'm going to have different equations because I'm not going to allow certain transitions. So you'll see that what will happen is that when I write the equations, and I'll do this again next time, when I write the equations for the case in which I'm on the boundary, this term and this term are not going to be in there because they're going to represent transitions that are not allowed. So there is no rate up from this state if J1 plus J2 adds up to S, because there's no room for anything. He goes away. Likewise, this term is not going to be in there. But also, that term isn't going to be in there because this is a state that's impossible. It's not allowed because it would correspond to S plus 1 customers. Similarly, this term is not allowed. But since this one corresponds to that one, and this one corresponds to that one, if that's not there, and that's not there, and that's not there, and that's not there, what remains is still satisfied by exactly the same solution. So even if I have a boundary, and even if the number of customers in each state from each stream are not independent of each other, nevertheless, I will still have a product solution. And you might think how that could be so if, in fact, the random variables are not independent. But we'll see that, in fact, we do have a product solution because it satisfies the equations. And then that will also give us some results that are kind of interesting because it'll show that the Erlang B model generalizes to the case in which I have an arbitrary number of streams of different types of traffic, and all I have to do to get the final answer is simply